Good morning, everyone. Welcome to the third day of POPL'. It is my great pleasure to introduce our keynote speaker for this morning. Jens Palsberg is a professor and former department chair of computer science at the University of California, Los Angeles. His research interests span the areas of programming languages, software engineering, and quantum computing. He is the director of the UCLA Amazon Science Hub for Humanity and Artificial Intelligence, an associate editor of ACM Transactions on Quantum Computing, and a member of the ACM Council. He is also a co-director of the Quantum Research Center at UCLA, which has more than 30 professors, and is on the team that started the master's degree in quantum science at UCLA. In 2012, he received the ACM SIGPlan Distinguished Service Award, and in 2023, he received a teaching award at UCLA for his course on quantum computing. And today he's here to tell us about Quantum 3.0, so let's give a warm welcome to Jens.
So welcome to Quantum 3.0. Last year saw a breakthrough in quantum error correction, and that started a new era of quantum computing research. And today I want to talk about the research challenges, and I want to persuade you that now is a great time to join. And I'm going to use 3 points to try to persuade you to join. The first point is that this breakthrough in quantum error correction makes computer science more important to quantum computing research. The second point is that this breakthrough creates an agenda of research, an agenda of essential computer science research that can help move the timeline for when quantum computing will succeed. And the third point is that the breakthrough will bolster the computer science quantum community, specifically the computer science quantum community. And so let me begin with my first point. 2024 was a great year for quantum computing research. And I want to make this point that the breakthrough in quantum error correction makes computer science more important to quantum. Actually, let's begin just with 2 points about quantum computing. A quantum computer is an accelerator, just like a GPU is an accelerator. It will get its work from a CPU, it will do some work, and it will pass results back to the CPU. It's a specialized accelerator. It's all about vectors and matrices, but it has something going for it, which is that a quantum computer can run quantum algorithms, some quantum algorithms that are exponentially faster than the classical ones. And so that's a very good way of being specialized. Whenever the quantum computer is good for something, that's when we will use it. And an exponential speed up is very much worth having. And the famous examples are, of course, number one, Shor's algorithm, exponentially faster factoring of integers on a quantum computer, which threatens to break public key crypto. And number two is simulation of physics at the level of atoms and molecules, which was the original vision of Feynman when he started to talk about quantum computing. And again, we will be able to simulate physics exponentially faster than what we can do on a classical computer. And that's the first point. It's something that if we can make that succeed, it will really be worth having. The second point is there's a difference between quantum computing and classical computing, well, in more than one sense, but certainly in this sense, which is that in quantum computing, error correction is a software problem. In this room, most of us are used to that. We can work on the software stack of our classical computers all day, and we never think about error correction, because error correction is in the hardware of classical computing. In quantum computing, it's different. In quantum computing, error correction has to be in the software stack. And the way it works is actually the way all error correction works. It's a question of adding redundancy so that when something goes wrong, we can look at the redundant information and work out what's going on and correct the errors. And the way this comes out in quantum computing is that we have the physical qubits. That's what the physics people are producing. They can be produced by many different technologies. Nowadays, we have a whole variety. One can make qubits with ion traps. One can make qubits with neutral atoms, with spin qubits, or there are superconducting qubits, and there are other emerging technologies. So there's a whole variety of hardware platform for making qubits. Those are the physical qubits. And then one has to realize that they are error-prone. They are kind of bad in the sense that if we start to do computation with them, the error rate is so high that the result will be meaningless. And so that's where error correction comes in, and it has to be in software. And so what that means is that we will use many physical qubits to protect a few good qubits, qubits that work like in the math book or in the POPL papers. We will call them logical qubits. So the ones that work perfectly. And then the idea is we will use many physical qubits to protect a few logical qubits. And we will do this protection using error correction exactly the way error correction normally works. And then one can add some skepticism here, which is, well, if we are doing this at the software level and the physical qubits are error-prone, doesn't that just mean that we are going to have very error-prone error correction and it will actually never work? And that's where we have to get to some skeptical points here and dive into this a little bit. So number one, does this work today? Does quantum computing, is it important for business and science today? No, that's years away. Number two, people, a skeptic might say, I have heard that this picture of yours from the previous slide actually is so bad that we need 1,000 physical qubits to support a single logical qubit. That sounds excessive. And indeed, that is a lot. And that is an estimate. That's the best estimate we have today for what we need. And that's a big factor to overcome. And it's definitely a big factor to overcome with adding so many error-prone physical qubits to support a single perfect logical qubit. So there's a problem there. And then there's a third question, which is that the skeptic might say, so how many logical, so let's say you can make logical qubits, but how many of them do you need? And even that question today is unclear. Some people might say 60. Other people will go as high as 1,000. And just to give you a sense, for Shor's algorithm, the best paper we have today is from 2021 by Craig Gidney and Martin Ekero that says that to run Shor's algorithm on an RSA integer of interest to breaking public key crypto, we will need 20 million physical qubits. So you can see even here, if we take the numbers on this slide and say 1,000 logical qubits, each supported by 1,000 physical qubits, that gets us to 1 million. There's still a jump up to 20 million from that paper. So we are talking about big numbers. And so the question is, can we ever make this work? And that's where 2024 comes in. And the question that we should ask ourselves really is the success of quantum computing, is that a physics problem? Or is it a computer science problem? And if it's a computer science problem, is it a programming languages problem? And if we just do a little bit of history, late 50s, Richard Feynman started to talk about the idea of having a quantum computer, and that would be a good idea for simulating physics. And then in the early 90s, Peter Shor invented Shor's algorithm for factoring integers. It was still all theory. I call that quantum 1.0. And then came the late 90s, where people from MIT invented the first quantum computer. So now we actually had some physical qubits, and quantum 2.0 started. Not very many physical qubits. Even today, we have hundreds or thousands of physical qubits on the largest quantum computers, and they're certainly error-prone. 5 years ago was the time when Google announced that they had done a computation on their quantum computer that a classical computer would need thousands of years to do. So we are rolling through quantum 2.0, and then we get to 2024, where people started to make experiments with error correction and show that all the theory we have had of error correction for decades start to work. And the way it starts to work is that we can start to suppress these errors that are there in the physical qubits, and we can start to actually, in a successful way, add the redundancy that we need to get to smaller error rates. And so I would say that what we have today is a few logical-ish qubits. There's still some error rate there, but so far we're just suppressing a little bit. And I'm going to show you how much, so you can make your own judgment here. I put 5 of my favorite papers from 2024 on this slide. I've been very sloppy with the authors. Many of these papers have many, many authors. And what I did to make it fit on a slide was simply to abbreviate a little bit and put the main company as I saw it among the authors on there. So we have papers from Google, from IBM, from Microsoft, from Continuum, from Coursera. And they have all demonstrated that we can suppress errors and that we can work towards building these logical qubits. And in more detail, I have the following extract from the papers. So all of these papers are experimental. And in the first data column there, I show the number of logical qubits. So you can see a small number, certainly not this end goal of 60 to 1,000 that I talked about, but we are sort of beginning to get there. The error rate is in the green column. And so there are two things to know about it, maybe three. The first thing is the error rate is sort of on the order of 10 to the minus 3, so let's call it 0.1% error rate, operating on the logical qubits. And so that's good. The second thing is that what they show is that they can make that error rate better than the error rate for the physical qubits. And the more aggressive error correction they add, the smaller the error rate. At the moment, because this is experimental, there's really a limit to how far we can go, for the simple reason that our quantum computers today only have hundreds or thousands of qubits. But what this is showing is a path towards the end goal, which, at least the way people talk about it today, is to have an error rate on the logical qubits of 10 to the minus 6. And then in the last column is the column that's like the 1,000 number that I had. How many physical qubits do we need to support each logical qubit? And you can see these numbers are not so high, that none of them are 1,000. And that's because the error correction is not as aggressive as what we would need in the future. But it's enough that we get some suppression of the error rate. And so I would say, as part of the computer science agenda that I'm going to advance today, is that we should be more optimistic than going for 1,000 physical qubits to support each logical qubit. We should go for 100. And this thing of optimizing and streamlining and improving things, that's something we can do. And I think we could get there. And so this leads me to the computer science agenda. And I'm going to try to make the point here that this breakthrough in quantum error correction creates an essential agenda where we, computer science, can help advance the timeline of when quantum computing will succeed. And this is my agenda slide here. So the absolutely key point is that the software stack of quantum computing must include error correction. And on the right, I am outlining such a stack. I made 3 levels to make it fit the slide and make it easy to talk about, and I will go into it a little bit. And then on the left are my agenda items. And so let's begin at the top. So a good software stack should have a good interface to the quantum algorithms people want to write. So we need to have a nice high-level language for writing Shor's algorithm and simulation of physics and all the other good algorithms that are coming out this decade. And that should be a level where we only talk about the logical qubits, and all the error correction should be hidden in the stack. And then the way it has to work is that there has to be a step of the compiler, which I here call decomposition and approximation, but where we're really compiling to an intermediate representation, which here I call the fault-tolerant gate set. And fault-tolerant gate set is another way of saying that what the quantum error correction people can do, both the experimental ones and the theoretical ones, is that they can support error correction for certain kinds of quantum gates. And we need to compile to that level. When you read quantum papers or quantum textbooks, you will see that quantum gates can be many different things. But for the purpose of actually error correcting them, so taking the gates and adding this sort of support layer of adding redundancy and doing all the things that need to be done, there's only a subset of those gates where people actually know how to do it. So we need to compile to that subset. That becomes the intermediate representation. And then the second level of the stack can then do all the things that we need for error correction. We need to encode the logical gates, so the gates that work on the logical qubits. We will need to add code for error detection and for error correction, and it will be a lot. There's no doubt that it'll be a lot, because if we're going to have 1,000, or with my optimism, 100 qubits to support each logical qubit, it's clear that this middle layer will add a whole lot of stuff. And so just to give you a sense, I attended a talk on quantum error correction a couple of years ago, and there's a very famous speaker who opened the talk by saying, "What is a quantum computer for?" And of course, nobody dares to say anything when this famous speaker asks a rhetorical question. So he continued by saying, well, you might think that it is for running quantum algorithms, but that would be wrong. Because if we're going to have 1,000 physical qubit to support each logical qubit. Think about it. If you have a quantum computer with 1 million qubits, 999,000 of those qubits are there just to protect 1,000 logical qubits. So actually, all the work is done, well, almost 99.9% of the work is done by code inserted by this middle layer of the software stack. The third layer of the software stack is kind of the rest, where we then compile this error-corrected stuff to the gate set of an actual quantum computer. And then we will have a full compiler. And so we have a compiler problem here. Clearly, the bottom layer needs to know the hardware really well. We definitely have an optimization problem here if we're going to decrease the resource need for supporting a logical qubit from a factor of 1,000 to a factor of 100. We should think about optimality, like we always do in computer science, to know when to stop. And then very importantly, verification. And so let me just dwell on this a bit. When we have a quantum computer running a quantum algorithm that gives us a quantum advantage, that is just faster, or maybe much faster than any classical computer can do, then knowing what's going on, knowing that we can trust the results, really comes down to ahead-of-time verification. We can no longer use a classical computer to simulate by definition because we have quantum advantage. And so we really need to verify that all of this stuff works, particularly that the error correction works, which where a lot of this stuff is. We need to verify the quantum algorithms, and we need to verify a lot of the math that's underlying, a lot of lemmas and things that are underlying all of those things. And so that is my agenda. And what is the problem here? The problem is that a lot of the research that have been going on so far have not exactly addressed the software problem with a software stack with error correction in the middle. And so what I'm setting out to do here in this part of the talk is to criticize some papers. And so just to avoid making too many more enemies today, I'm going to criticize my own papers. I'm going to start with something straightforward, which is conditionals. So quantum computing needs conditionals just as much as classical computing does. But there's a difference. So the second big difference today, quantum conditionals are hard to compile. And classical conditions are easy to compile. Okay, so here's a classical condition. We have a conditional where the condition is B0 and B1. There's two booleans. And one way to compile this is we could make sort of a straightforward cascade of ifs. If the first boolean, then if the second boolean, and then we can do our thing. That gives, if you expand this to n conjuncts, you will get code of linear size, of course. And the overhead is very small to make this happen in machine code. For quantum, if you try to do a similar thing, you will end up with code of exponential size in n. And so that's not good. So that's already like a problem. So what can one do? So here comes just an example of one of the things one can do in quantum. Whenever you have an instruction in quantum, you can also have the square root of that instruction. And so I took the example from the previous page, and then I just rewrote it with q's instead of b. So now it looks more quantum-ish. We have a condition with q0 and q1. And then, so those are both qubits. And then I want to do an X gate on qubit number 2. And so we should not compile this to this cascade of ifs that I showed before. But what one could imagine is to do the following. Let's do like this linear sequence of ifs where we do an if on the first qubit and an if on the second qubit. And then we get the idea of doing square root of X. And it's not a bad idea, because if both q0 and q1 are 0, then nothing will happen, which is correct. And if both q0 and q1 are 1, then each of those two ifs on the right will do square root of X on q2. And really what will happen is, after both these instructions go, we will have square root of X times square root of X, and we will have the net effect of X. So the point is they get multiplied together. A lot of stuff in quantum computing is about multiplication. However, the problem is that if q0 is 1 and q1 is 0, or the other way around, just one of them is 0, then we'll end up just doing square root of X one time. That's not good. That's neither here nor there. However, it turns out that one can fix this, and so that was something we were working on. So we take the same two instructions, and then we do a little trick. And I want to, let's call it a technique. That sounds much better. So we'll do something that I'll just go through just to give you a little bit of sense of how reasoning in quantum computing goes. So the table at the bottom is supposed to illustrate that this code works for all cases. So the first thing to know is that quantum computing is applied linear algebra, and so it means that all we need to work with are basis vectors. If we can show that everything works for basis vectors, it always works. And so in this case here, that turns out to mean that here, if you look at the first column at the bottom, that if we can look at Q0 and Q1 and just think about the cases 0, 0, 0, 1, 1, 0, 1, 1, we are good. If everything works for those 4 cases, linear algebra takes care of the rest. And then now comes the second point. I'm going to think of Q0 and Q1 as a binary number in, actually, it's like a binary number with 2 bits. So it's 0, 1, 2, 3, I guess one could say. That's how I'll think about it. Written in binary. And the least significant bit is Q0, and the most significant bit is Q1. And so then what I will actually do down here is that I'm going to write Q1 first. So when you see this 0, 0 here, it's actually first Q1 and then Q0. That'll just make all the reasoning go very nicely here. So this thing of using sort of binary notation for numbers, that happens all the time in quantum computing. So I had to get used to that at some point. So here we go. So we have these 5 lines of code, and you can see there are 5 columns, each for each one. And when we get to the last column, we have executed all of this code. So the trick that we are using here is that there's some +1, -1 going on, mod 4. So we're taking this 2-bit number, and we're going to do +1 and -1. And and then there's this last thing to note, which is you can see this is a dagger, square root dagger. That's quantum notation for inverse. So it's like going back. Instead of doing square root, we are kind of like taking away a square root. And so it goes as follows. So let's look at some cases. So 0, 0. So we just do like back of the envelope here. So we start with 0, 0. So both of the Q0 and Q1 are 0. Then if Q0 will do nothing, if Q1 will do nothing, then we will say Q1, Q0 +1. Well, so now we go from 0, 0, that's 0. +1 is 1. And so that means that the bit pattern is now 0, 1. Q1 is still 0, so that does nothing. And then we subtract, and we are back to our bit pattern from before. So absolutely nothing happened. And that's what you see here. We are in 0, 0. Another easy-ish case, but more interesting, is 1, 1. Let me go to that one. 1, 1 says, OK, now both the qubits are 1. So it means that we will do what I said before. If Q0 is 1, we do square root of x. If Q1 is 1, we do square root of x. Now we have done x. So that's why down here we land on x applied to Q2. So then comes the rest. So we add 1, modulo 4. So this bit pattern 1, 1 gets changed to 0, 0 after the mod 4 kicks in. And then at that point, both the qubits are 0. So if Q1 does nothing, and then we can subtract, and we get back to our bit pattern before, and the net effect was that we got an x. So we disturbed nothing. I added 3 lines of code, but it still works on the 2 cases that worked before. So that's good news. Now I will show one of the other 2 cases, and you will see that it's still, that now there's an improvement. So let's do this bit pattern 0, 1. So Q0 is 1, so we do square root of x. And then Q1 is still 0, so we do nothing. And then we do +1. So we get the bit pattern changed from 0, 1, which represents 1, to 1, 0, which represents 2. And so at that point, Q1 is 1. And then we take away 1 square root of x, and we are back to just Q2, and nothing happened. And so somehow this +1 minus thing, +1 minus 1 thing, just solves all our problems, and it works beautifully for the case of 1, 0 as well. And so, so this works for the case of this conditional, and it turns out that it generalizes. And all this +1 minus 1 business can also be done in a way that is linear. And so we end up with linear code for this case. And just as an aside, I want to show you how a circuit can look. So here's a quantum circuit that does exactly what we had before. You can see we have some gates there. So you notice that I call the qubits A, B, and C. In this case, we have some gates here that touch 2 qubits. They all touch 2 qubits. In fact, some of them touch AC, some of them touch BC, and some of them touch AB. So they're all 2-qubit gates. But the key thing is that the scheme generalizes, and we end up with no less than 278 times n for a conditional with n, what is that? N conjuncts in the condition. That is a big number, and kind of depressing to think about is that the best known lower bound from the theoreticians is 2n. So there's a big gap there. But just to tell you, things used to be quite a lot worse. Until recently, Qiskit, which is IBM's open source software stack for quantum, would give you an exponential number of gates. So that's actually the green line here, where we kind of have the number of conjuncts on the x-axis and the total number of gates on the y-axis. If we go to the Nielsen and Chuang book from 2000, which is usually called the Bible of Quantum Computing, the best they had in that book was actually n squared number of gates. That's the yellow line here. Then, as it happened 10 years ago, Craig Gidney published the first linear compilation algorithm. That's the red line here, and then finally we get what we have here. But you can see 278 times n. It's still a lot. IBM is now implementing our scheme, and it goes into Qiskit. So now, either now or very soon, you will get a linear number of gates when you use conditionals in Qiskit. The problem is that all this is no good for the new agenda for quantum computing, computer science research, because there's no error correction here. If we think in terms of the software stack, what we are doing is that we are compiling directly from a source level, quantum algorithm level, conditional, directly to the hardware gates. And there's no error correction in the middle. And so it means that if we are going to have real, honest-to-God, error-corrected conditionals, we need to figure out how to factor this through the intermediate representation and eventually get the whole software stack going. So there's a whole research agenda there. So we need more papers on quantum conditionals. All right, second point I want to bring up is optimization. So you know, Andrew Appel has the full employment theorem for compiler researchers. There's also a full employment theorem for quantum tools researchers. In this case, it goes as follows. The basic theorem is that if you give me a quantum circuit, for me to find out if that quantum circuit implements the identity function, does absolutely nothing, is QMA complete. QMA is the complexity class that's the quantum sister of NP complete. And so QMA complete is like harder than NP complete. And so what this implies is the corollary that both optimization and verification of quantum circuits is QMA hard. And that's the full employment theorem, because it means that now we can build optimizers and verifiers until the cows come home, and we can just keep improving them. And indeed, there are lots of quantum circuit optimizers out there. I listed eight of them here for 8 of my favorite ones. There are many more, and they are very interesting and different in interesting ways. The one I was working on is quartz, the one second from the bottom, and we had a particular angle on things that I want to talk about today, but there are many more angles on quantum optimization that are in these other tools that we don't cover. So our angle was to say, from math, we get identities between products of matrices, here written as circuit identities. So really what you see on each of these identities is a little product of matrices that's equal to another product of matrices. And now, once we have bunches of these, one can start to say, let's use them to optimize. So at the bottom here, I'm using some of the rules above, and one could say, well, so here we have a circuit with 4 gates as it is. That's how the count comes out. And then we could apply a rule, and we could apply another couple of rules, and then you can see over here we have only 3 gates. That's an improvement. We should just do more of that. And now it sounds intuitive that the more rules we have, the more we should be able to do. And so the idea we got in Quartz was, let's just generate all of them, all the rules. And so we set up the following generation scheme. What it does is to say we have this sort of syntactic idea of what an identity could look like between 2 matrix products, or two circuits. And let's just put down n, the number of qubits that we will deal with in this identity. And Q, that would be the number of gates on each side of the equation. And let's just generate everything up to that size. And then whatever we generate, we will pass it through C3 to see if it's a valid identity. And if it is, now we have a lot of rules. And then in the pruning step down here, what we will do is we will prune away all the identities that are implied by some other identities and just like pare it down to a really core set that has no redundancy in it. And then once you have these rules, you can just feed them to the optimizer. And now hopefully there we got a lot of rules. And then the optimizer can do a really good job. Actually, yes, we get a lot of rules. Already up to 3 qubits. And this is for a particular set of gates. So this is how it works in quantum computing. You have to fix the gates that we can work with. You can either take the gate set from a particular quantum computer, or you can take the gate set that the theoreticians find interesting. And for a particular gate set here, we got for already up to 7 gates on each side of an equation with just 3 qubits in the picture, more than 300,000 transformations. And now the number of transformations is so big that now it becomes like a time problem for the compiler to go through them. There's just too many. And so the compiler will have to pick some. And now there's this whole sort of a follow-up line of research on how do you pick the best transformation. So one paper I know uses reinforcement learning to learn which transformations to use when. Very fruitful. I will just talk about the quartz results as we had them. And so what we did was that we used a very, by now, standard benchmark set from Matthew Amy and company from 10 years ago that many people use. There are 26 circuits in there, and we optimize. You can see how many gates are there, just to get a sense of we are trying to optimize the number of gates. And then we go through some different optimizer. Here's Qiskit, as straight up as it is from IBM. Then there's this paper from mainly from Maryland from 2018 that I think is a wonderful paper. Here's the Vox paper from POPL 2021 that did the first verified quantum compiler. And then we have the quartz results over here. And what we do is we add a little bit more than what I said. We also have some static analysis-based optimization that gives the first 19% of improvement. And then we add all these local rules with heuristics for picking some of them to optimize. And we get up to a 29% reduction in gates. And so that's what it is. But of course, there's no error correction in this picture at all. What we really need to do is to have an optimization story for a quantum software stack where the optimization of error correction gets special attention. And the reason why this is not just one more case of something general, it turns out that the software that we need for doing quantum error correction is actually a little bit specialized. It is very specialized in terms of the gates that it uses and the way that it works. And I think there are huge opportunities for optimization there that we just don't really think about when we try to optimize a general quantum circuit. And so we need to get good at that. So if we have nothing like that, we need more papers on quantum optimization. Then let me move on and talk about optimality a little bit. So I showed you this circuit before, and it's actually optimal in a certain sense. I will tell you which sense. So what we have is a conditional. One can also write the conditional the way it is on the left, which is very compact. And what you see on the right are these 5 2-qubit gates. So 5 gates that each touch 2 qubits. And it turns out that if all we're interested in is to count 2-qubit gates, which is a good idea, because on a typical quantum computer, that's the slowest kind of gates. They're slower than the 1-qubit gates. 5 is what we need. You cannot do it with 4. And that was a theorem that came out in 10 years ago. Apparently, a lot happened 10 years ago. And that theorem was like 2.5 pages in a physics journal. That was a paper by Minxin Ying and Nenkung Yu. And I love that paper, and I decided I'm going to learn the proof. And so what happened there was that I found out about the paper on a Saturday, and I thought, oh, this is a quick proof of a beautiful theorem. I'm going to learn the proof, and then I'm going to give a lecture about it on Tuesday, because I'm a little short on lecture material for my class. Okay, so 100 or more 1-hour Zoom calls later with Nenkung, we finally had a write-up in LaTeX. And in our version, which we published in a math journal last year, it's 60 pages of LaTeX. And I'm showing you the structure of the proof here just to give you a sense that there's a lot going on. one could think that, oh, this is just like many, many cases that are all very similar, but it's like, no, there are only 2 cases in the proof, and everything is very different from everything else. My students formalized most of this proof in Coq, and it's 16,000 lines, building on top of Robert Rand's library of QuantumLib, which has a lot more lines in it. And so in total, there's a lot going on. And so what I got out of this is that there's a huge potential here for formalizing not just the quantum algorithms and the quantum compilers, but also some of the math that's underlying. And that I think is a quest that the whole verification part of the community can take up. But I also want to talk about optimality in a different way. Once we move down further towards the bottom of the software stack, we get to where the physical gates of the quantum computer live. And at that level, we have to realize that on some qubit technologies, you cannot do 2-qubit gates on any 2 qubits. There are restrictions. And I'm trying to illustrate the restrictions here. Oftentimes, you will find that there are 3 qubits you want to work with, and actually, even if they're quite close together, only 2 pairs are connected, and the 3rd pair isn't. And so you can imagine for my conditional, where I'm using 3 qubits, this is like a pain, because this optimal circuit I showed is using both AB, AC, and BC. But then if you don't get all of them, what are you going to do? And so some programming comes in, and so I have this picture here where I focus on, suppose we can only do 2-qubit gates on A and C and B and C. And so then what we can do is we can program a little bit. And what I'm actually doing here is I'm taking the circuit that I had before, and then I'm saying, well, so now we cannot do AC. And the AC gate was sitting sort of here where I'm circling. And what I will do is I will insert 2 swap gates. That's the 2 funny ones with X connected here, some X is connected, and then I make some changes, and now what I have is a circuit that, if you just think about it for 2 minutes, does exactly what the circuit did before. But now what you see is, first of all, there are no gates that connect from A and C, from A to C, so that's good. And second, we have a couple of gates here that both work on B and C, and those could be combined. And so we are down to 1, 2, 3, 4, 5, 6 gates, and that's actually optimal. And so we took it upon ourselves to prove that is optimal, and now we actually built on this previous paper in terms of the proofs, and so now there's more stuff. And just to give you a sense of how this works, if you look at it from a particular angle, which is to say what we really need to focus on are 8x8 matrices that are diagonal. So that kind of represents a particular kind of operations that work on 3 qubits. In this case, it's a conditional on 3 qubits that we are interested in. Then it turns out that what you can do with 4 2-qubit gates that work on any combination of AB, AC, BC is just the same as you can do if you are restricted to 4 neighbor gates in terms of one of these 3 pictures that I showed, which is again the same as what you can do with 5 neighbor gates. And so one of the implications here is that it makes no difference whether you have 4 neighbor gates or 5 neighbor gates. You can do the same if what you want to do is implement a conditional in particular, which is kind of surprising, but that's how it goes. And so you can imagine, again, we're very suspicious about whether this was correct. And so there's this whole effort, again, to verify all of this in Coq to see that it works. And so I think there are many things like this that have a direct bearing on how we compile our things and what is the quantum theories that we build on. The more of that we can get verified, the better. And in particular, quantum error correction is going to explode in research over the next 5 years. And there will be so much new stuff there, new error correction techniques, new optimization techniques, and it will be very difficult to experiment with that and be confident. The right way to go is to verify that stuff. So we need a whole verification agenda there. That finishes my second point. And now I want to dwell on the point that this breakthrough in quantum error correction will bolster the computer science community. And I went to CS rankings, so thanks to Emery Berger, and simply looked up in the CS rankings conferences how many papers had quantum in the title. So it's not perfect. I know there are papers on quantum that don't have quantum in the title, but that was easy for me to do. And here's the count for 2020, 21, 22, 23, 24. So 5 full years, calendar years. And there are almost 700 papers represented here. And you can see it's growing. It's very clear that even until this breakthrough year of 2024, this is growing. And I fully expect that now it's going to grow more. I want to give you a little bit of a breakdown. So if we take these papers and look where the center of gravity is, the center of gravity is not so far away from programming languages. And most of the, I must say, the biggest chunk of papers are up towards the top of this picture. Theory, Fox, Soda, Stock. There are more than 100 papers the last 5 years that have quantum in the title. The hardware conferences, I think, naturally have many quantum papers because I think the hardware, to me, is like, that's as close as one gets to sort of the whole physics agenda that has been going for a long time. So both the design automation, DAC, had almost 100 papers. And then the more sort of architecture level, ASP+, ISCA, and so on, again, almost 100 papers. And then we get to crypto. So along with this agenda of advancing quantum computing and making quantum computing succeed, there's also the worry that one day it may succeed. And then what do we do with all the crypto when Shor's algorithm starts to work? And that's where the post-quantum crypto comes in. And you can see both crypto and Eurocrypt, many papers, again, almost 100 papers. That's one of the things they're working on there. And then for machine learning, it's actually quite natural that ICML and NeurIPS would have many papers because multiple reasons. One is quantum computing is applied linear algebra. A lot of machine learning is applied linear algebra. And so it seems like a match made in heaven to invent quantum machine learning. And there's a lot of people working on that. But second, of course, one could also imagine machine learning techniques that will help us make the software stack of quantum computing better. There's a lot of other work on that. And then we get to the programming languages. And as it happens, PLDI, POPL, and UPSLA have had an even smattering of quantum papers over the last 5 years. And you can see here figures prominently in this list. And I think that we are at the point where quantum computing is seeing now that computer science will be more important to quantum computing. And I think that the agenda I'm outlining here will make programming languages very core to the next agenda for research in quantum computing here. I want to do a little bit of United States-centric stuff because that's where I live. There's a lot of investment going on. So there's a lot of national investment going on in other countries as well. I just want to touch on United States. Most recently, the National Science Foundation started the NQVL program last year. There are 11 projects. Those projects are 6 of them are in quantum computing, 3 of them are in quantum sensing, and 2 of them are in quantum networking. And they are all designed to be 8-year projects. So I'm outlining below how those 11 projects get some money in the first year, then they get down-selected, then they get more money in the next 2 years, and then they get down-selected again, and then they get even more money in the next 5 years. And say again? That's very strange. Can we complain to the AV people? Do you think the adapter has the problem? Oh. That's amazing. How is that possible?
It's a magic trick.
No, but now plug it in again, and then let's see. So that's very curious. So you should think that this is running quantum computing, but it isn't. So I can no longer change the slides here. So I can see the AV people are working hard back there. Hey.
We tried unplugging and replugging.
Yeah. Anyway, but let me tell you that the project I'm in is a project led by a physics professor at UCLA and with participation from Berkeley, from UCSD, from other places, and our industry partner is Continuum. And I guess our ultimate goal is, after 8 years, we will produce a quantum computer with 60 logical qubits. And a lot of the research agenda is like the research agenda that I'm outlining here, that we need a software stack that has error correction in it, and that there are many problems to solve if we are going to get to 60 logical qubits. And what I see around the world is that there are these investments that are happening from national governments everywhere. And I think it's an exciting time that in computer science we can certainly at a more regional level than the national government. I want to also add a little bit about, okay, so I have a picture of the mall. So that's a picture of the mall where the quantum research are going to move once they've done a little bit of refurbishing inside. But let me for a moment also talk to the education people in the audience, to the academics. So for me, this is not just a research agenda. In 2019, I was on my way to POPL. I ordered Min-Cheng Yang's book. And on quantum computing, I came back, there was the book, I started reading, and the next day I sent email to all the people in my department saying, starting April 1st, I will teach a course on quantum computing. And that puts pressure on me, in particular because within an hour I got email from 2 of my colleagues saying, I have changed my schedule so I can attend your lectures. And so the next 2 months, I was learning quantum computing as fast as I could. And by now, I have two courses in a sequence, Quantum 1 and Quantum 2. I call it Quantum Programming and Quantum Algorithms, 10 weeks, each of them. And more than 450 students have come through Quantum Programming, and more than 130 students have then stayed on and taken Quantum Algorithms. And it's wonderful. So it's a wonderful experience with just hearing all the different backgrounds and knowledge that people have. And in particular, because we also started this quantum science degree, which is housed in physics, but also has participation from computer science, particularly from me. It means that I have students in the class from certainly computer science and physics and math and chemistry and some engineering departments. And it's just wonderful with all this background. And it makes for an interesting challenge of communicating with all these people about the technicalities of quantum. And then one last thing. Some of us are trying to convince the National Science Foundation to start a program in computer science with money for quantum research. And to that end, we are planning a workshop in the late summer where the goal is to write down a computer science research agenda for quantum for the next 5 or 10 years. And I hope that some of you will be able to attend. And if you want to, please talk to me. And so that brings me to the end. So here's my research agenda. I believe that computer science research, that we are starting to near critical mass, where we can submit and publish our papers in computer science venues, have our papers reviewed by our peers, where we have enough critical mass that a computer science paper can get reviewed by computer science experts on quantum. And then we have a whole agenda in front of us, which I think is going to create a lot more energy for the computer science people working on quantum computing. And I think that together we can advance the timeline and make quantum computing succeed sooner than it would otherwise. Thank you.
Thank you for the talk. We have plenty of time for questions.
Thank you for the great talk, Jens. In my personal experience, working in this area benefits from, if not requires, communicating with theorists, devices people, architects, a whole lot of people that PL folks might have some language barriers with. How do you think that as a community we can overcome this and make sure that we're always working on relevant and timely topics?
I think that the language barrier is real, and I certainly experience it in my teaching. But I also, because of the collaborations I'm in, I get to talk to physics people and chemistry people all the time, and the language barrier is there. And it's not just talking, but it's also reading the papers that, for example, come out of physics. They're written in what I would say, it's written in a different way. And it takes time to just get in and understand that they're making assumptions that is known to everyone in physics, but they're not known to me. And so I think, as with all other collaborations that are interdisciplinary, this thing of getting together and staying together, that's the key. And take the time to talk long enough that a common vocabulary emerges. That, I think, is the key. And so I have had the good fortune to, for example, get involved in the largest quantum computing research center in the United States, which is housed at Berkeley. It's run by a person in physics, but they somehow took me on board 5 years ago, and we have been able to just keep talking. And I start to learn what they're saying, and maybe they start to learn a little bit what I'm saying, and we can do things together. So getting together and staying together is the key.
Couldn't agree more. Let's do more of that. Thanks.
So I've been trying to relate the examples you're showing us to classical examples to understand better how we think about optimization here. What you told us about seems to be focused on kind of an analog of improving area of a classical circuit. Okay. But a big concern for classical circuits is parallelism and reducing the length of the longest sequential chain, which you didn't mention here. Right. Is that also a concern in this domain?
It is a concern, but I think that it is beginning to be less of a concern for the reason that when quantum error correction starts to work, then decoherence, which sort of threatens to just put a full stop to quantum at some point, starts to be less of a concern because decoherence just becomes one more error that error correction is supposed to deal with. So I would say that the raw number of gates is beginning to be more of a concern than the just actual depth of the circuit. Every time we execute a gate, it introduces errors that have to be corrected.
There isn't a concern with reducing the latency of getting the final answer back?
Oh, that is a good question. So I think that we are always interested in time to compute. But given all the other problems in quantum computing, I think that that's sort of a little bit down the list of priorities, but that is always a concern. Anyone who can do worst-case execution time for quantum computing, that will be super welcome.
And when the community gets to working on that, will it look like trying to create more parallel classical circuits in some sense?
Yes, I think that parallelism really for these quantum circuits that I draw is simply a matter of gates that are sort of stacked on top of each other. And the more we can do of that, the better. And indeed, I remember yesterday I was just online in my class, being here in Denver, giving a talk about Hamiltonian simulation, about simulation of physics. And there's a very nice case there where it looks like the depth will be very big, but just with a little bit of human smartness, you can make the depth almost nothing. If we can get compilers to automate that, wonderful.
Thank you.
Your presentation of like how quantum error correction interacts with these algorithms, you said it was a sort of a software problem, and I was thinking that this would come out sort of similar to how concurrency is treated in modern classical computing, where it's now partially the source level, user program level concern. It's not something that we can just ignore and hope that the compiler solves it for us. But here, this pipeline is still separating the concerns of quantum error correction into a layer of the stack, and then we're just programming something for the logical qubits at the user level. Do you think that this could be improved by like having the, divesting some of the responsibility for doing error correction, or at least error correction friendly techniques to the programmer?
I understand. It's a very good point, and I like the summary very much. I have two or maybe three things I want to say. The first is, I think that we are sort of in this sort of same dreamland as concurrency was 30 years ago, where the dream was that you write your sequential program and the compiler makes everything nice and parallel and much faster. And then it turns out that it's not always so easy, and the programmer has to get more involved. I think that we may very well one day end up in what you're saying is that this dream of writing the software stack this way doesn't quite give us everything we want, and we need the programmer to be more involved in saying something about where the error correction goes. The second point is that maybe we should go further than what you're saying. People are talking about hardware-software co-design in this whole quantum area where maybe we should go all the way and look at how the qubits are architected together, what is connected to what, because if you do it this way, it's great for this algorithm. If you do it this way, it's great for that algorithm. And then it's even more aggressive programmer involvement than what you were saying. I think there's going to be a lot of work in these directions the next 10 years.
Jens, thanks for a wonderful talk. This is Kedar Namjoshi from Bell Labs. So I want to actually go back to the hardware. So I get your point about the software, and computer science being important. But if you think back to the history of classical computing, hardware in the 1950s was very error-prone to the extent that, John von Neumann wrote this classic paper on how to build reliable systems out of unreliable components. So my question is sort of, where is the hardware going? Like, is it getting, significantly better at reducing faults? And the second question is, do the physicists have something like the Shannon theorem that says you can't get beyond a certain point? You can't sort of reduce are there sort of fundamental limits on how low the error can get?
Very good. Excellent point. So let's see. So two things. So the first is, so clearly we can hope for better physical qubits with lower error rate. And my understanding is that the quantum computers are getting better and better on that front. Most recently, we saw the announcement Google have this new Willow chip, which is very, very good and has a very low error rate compared to some previous ones. And so that is saying that clearly when the physical qubits get better, we may either have the error correction algorithms that we had in mind do even better, or we may need less error correction to get to the same endpoint that we had in mind. And so in that sense, I think error correction and better physical qubits are just working hand in hand. And so the physics people are working over there, and the computer science people can work over here, and it's synergy. The second point about whether there's a limit, I actually don't know. So here my knowledge of physics ends, and I cannot give the answer. And I hope that there will be physics people that can fill that in at some point.
I have a quick question. You had a square root, and that makes me nervous.
Yeah.
So do quantum computers manipulate reals or some kind of flows?
Very good. So quantum computing manipulates a vector of complex numbers. And so the state...
Number, they are built out of reals? Or?
Yes, the complex numbers build out of reals, for sure. And so I managed to sort of hide this under the hood the whole talk. But the state vector of a quantum computer is a unit vector of complex numbers. And each individual step of the quantum computer, all it does is to take you from one unit vector of complex numbers to another unit vector of complex numbers. It's a very long unit vector, because if you have n qubits, you actually have 2 to the n complex numbers. And so if you had 300 qubits, which some quantum computers today already have, you have 2 to the 300 complex numbers, which is more complex numbers than there are atoms in the known universe. And so it's just like very long unit vectors. And but back to the square roots, because we have complex numbers, we can do square roots. Complex numbers have square roots, and matrices built out of complex numbers have square roots. Everything is very flexible there.
What do you think? Testing. 7 assistants to ask my question here. What do you think the societal consequences will be of succeeding in this endeavor? And why aren't you concerned about those, or how do you think we'll mitigate them? And do I really want to be involved in this enterprise?
Very, very good. I will just outline a bit of what the sort of the overall hope for the quantum computing area is. I would say that when we go to the physics simulation, the areas that will benefit from that will be material science, chemistry, also some basic physics, where they want to design new materials or design better batteries or design better things where you really need to be working at the atomic level, and where more computing would be better, where people are essentially just hemmed in by that they don't have enough computing power with classical computers, and they would be able to do more and better designs if they had quantum computers. The second one is, of course, Shor's algorithm, which is, in the first story is kind of happy. The second, the Shor's algorithm, that's kind of a sad story, because that will mean that you can read my credit card. And you'll just break the crypto when I access the bank, and then it's not good. So that's kind of a sad story. And that's why we need post-quantum crypto, to be sure that if quantum computing succeeds, then we have something going on. But I think that as an intellectual endeavor of even making Shor's algorithm run on integers we cannot factor today, that's still a good intellectual endeavor, but just a little bit of a sad outcome.
All right, with that, let's thank Jens again and move to the coffee break.
Thank you.